Now, for most functions, and for us, we'll be dealing with a function that's continuous mostly at all points, right? In R2 R3. Okay. Now there's a theorem which we call Clothes theorem. It states that suppose that f is defined on a disk that contains the points a and b. If the functions fx and fy are continuous on this disk, then we say that f of x, y, f of xy is equal to, at ab, is equal to f of yx at ab. Now, this is not always the case, except where the function is continuous on the disk at the point a and b. Or I know that's confusing, but let's say unless the function is continuous at the point a and b, right? It's both continuous here and continuous there. It's going to be equal. Okay, let's take an example. If you have f of x, y is equal to xe minus x squared y squared, right? Then we want to verify Clothes theorem. So we find fx of that. Then we want to put that true. Differentiate this with respect to, when I hold this one constant and differentiate that, I'm going to get minus 2x, multiply my x in front, e minus x squared y squared, plus hold this constant, differentiate this, and I'm going to get e minus x squared y squared. Simplifying it, I'm going to get 2x squared e minus x squared y squared plus e minus x squared y squared. Now if I find fy, if I differentiate this with respect to y, I'm going to get 2xy e minus x squared y squared. Okay, so I need fxy, sorry. What it means is that I'm going to differentiate this y here with respect to x. Now, y with respect to x, I'm going to still use product rule, right? I hold 2xy constant and differentiate this. I'm going to get e minus s squared y squared. The top with respect to x, remember, is going to give me minus 2x plus, I'm going to hold this one constant now, e minus s squared y squared, and differentiate this with respect to x, and I'm going to get 2y. If I simplify, I get minus 4 s squared y e minus x squared y squared plus 2y e minus s squared y squared. And if I find fxy, please forgive me, okay? This one is f. Yes, I differentiate y with respect to x. Good. I'm going to differentiate x with respect to y. If I differentiate this one here with respect to y, I'm going to use product rule for the one here in front, right? So I hold 2 x squared constant, differentiate that, I'm going to get minus 2x sorry, I'm differentiating this with respect to y. It's with respect to y. So with respect to y, this one here goes straight away, right? There is no y here. So there is y there. Y is going to come forward. So I'm going to get 2y times 2x squared e minus x squared y squared plus differentiate this with respect to y, and it's going to give you 2y e minus x squared y squared. If I simplify, I'm going to get 4x squared y e minus x squared y squared plus 2y e minus x squared y squared. So clearly you can see that this one here is equal to the one, right? Now it's solved on the slide, so you should be fine. And please, on the slides, I don't know, there's some correct, please do the corrections. Let me see. Please note that on the slides, there are some corrections, so please, you do the corrections. I can see them, I don't know about you. Okay. Still moving on higher order derivatives. We want to find f x y is xx, y z for fx y z is equal to z cubed y squared in x. Now here find fx, and fx is going to give me z3 y squared. When I differentiate ln, I get 1 over x, so to divide. And I want to find fxx. I differentiate this again with respect to x. Now this can be written as z3 y squared x to the power minus 1. So here, minus 1 will come forward. I'm going to get minus z3 y2 x, take minus 1 and I get minus 2. And I want to rewrite this as minus z3 y2 all over x2. Next, I want to find fx xy. fxxy, and I differentiate this with respect to y, and I'm going to have minus 2 z3 y will reduce now all over x squared, and I can now differentiate find fxxyz. Differentiate this with respect to z, and I have minus 6 z squared. What will go back? That, and I cannot find my fxx y z z. Differentiate this with respect to z now, and I get minus 12 z y all over x squared. Okay. Now we go to what we call differentials or total differential. What we find fx is the rate of change if a function, right, f depends on x and y, then fx is the rate of, one just look at the rate of change of the function with respect to x, keeping y fixed. And fy will also be the rate of change of the function with respect to y, keeping x fixed. If we want to look at the total rate of change, which we call the f, then it's just going to be fx dx plus fy dy. This we call total rate of change. Let's look at an example. If f of x y is equal to 3x squared y 7, then the f, which is the total rate of change, right, we said was fx dx plus fy dy. Now fx here is 6x y7 and fy is 21x squared y6. So my df is just fx, which is 6x y7 dx plus fy, which is 21x squared y6 dy. That is my total rate of change. I hope you understand that one. Okay.